Alright guys, just wanted to talk to you about another example. Trying a new format here. So these are from my notes, obviously. So here we have the matrix 0, 0, minus 4, 2, 4, 2. Example 11.4.7. This is on page, what page is this thing on? 289, or around about there. I'm not sure which version this is. You might have noticed the page numbers jump about a bit since I've been taking Dr. Professor Landon's corrections to heart. Anyway, so you calculate the determinant of a minus lambda I, and you can, if you expand on this, it pops out this 4 minus lambda, and you're left with the outer corners as the only interesting subdeterminant, because the other ones are 0 in the expansion. So that gives us lambda times 6 minus lambda, and rather minus lambda, and then minus 4 times 2, which just gives me 8. And as you can see, that gives me 4 lambda minus 4 squared and lambda minus 2, which means that 4 is an eigenvalue with multiplicity algebraic multiplicity 2, and 2 is an eigenvalue with algebraic multiplicity 1. Okay, so then we go to the next page where I calculate the eigenvectors, and you notice here, to start with, the calculation for the eigenvalue 2, we just basically have to do row reduction. I skipped the steps here basically, but you can see what happens is we just get this, at which point we see we got aha. So there's our typical, a nice basis for the 2 eigenspace is just minus 2, 1, 1. Great. And that's enough. I mean, there's just an algebraic multiplicity 1 there, so that's all you can expect. Algebraic multiplicity 2, there's actually 2 different things that could happen. You might only find 1 eigenvector, or you might find 2. In this case, we actually find 2, and here's how it goes. So we calculate the reduced row echelon form of A minus 4i. That gives me this matrix, but as you can see, it's just the same equation 1, 2, 3 times. That reduces to this, which gives me basically the single equation u plus w equal to 0. You can choose, so basically that makes u equal to minus w, and v is free. So scroll down here, that gives us a 2-dimensional null space, so the geometric multiplicity of this eigenspace is in fact 2. As you can see, these guys are your basis for the 4 eigenspace, I should say. And there you go. Now this is a matrix with 3 linearly independent eigenvectors. Consequently, A is diagonalizable, and that's all I got for you on this one, guys. I think there's another example somewhere later in the notes, though, where we have a repeated, well, I mean, you've seen it in the 2x2 case already. Just because you have a repeated eigenvalue, it doesn't mean that you get 2 eigenvectors. We saw that back in the 2x2 case and the ones I actually went over in the in-class lecture. And that's all I got for you.